Good afternoon. Thank you very much, everyone, for attending my PhD final presentation entitled Development of Chitosan-based Nanocomposite enriched with essential oil as antifungal coating for fresh fruit application. My name is Atta Aditya Wardana, under supervision of Professor Fumiko Tanaka and Assistant Professor Fumila Tanaka. The contents of this presentation consists of an introduction, then chapter 2, chapter 3, and chapter 4 is regarding my research during my PhD study. And then the last chapter is about conclusion and future works. Chapter 1, introduction. Fruit quality is the most essential parameter in the selection of food. Global food waste reported that approximately 1.3 billion tons of food is wasted every year. As seen in this figure, fruit and vegetables is the highest one because high moisture content. Okawa reported that the fungal decay is the most extensive cause, about 30% of food loss during post-harvest handling. Animal coating and film technology has emerged as a potential alternative. It's usually fabricated from polysaccharide, lipid, protein, and food additive such as flavor and aroma compounds, antioxidants, antimicrobials, and nanoparticles. In this study, we use chitosan and nanoparticle to produce a nanocomposite, and then to improve the performance, the essential oil also was added. The objective of this research are to develop antifungal nanocomposite coating formulated from chitosan, Indonesia origin essential oil and nanoparticles, and to characterize the functional properties of the coating film, and to facilitate the development of food-grade nanocomposite coating film suitable for fresh fruit application. Moving on to chapter 2, about the antifungal effect against Penicillium italicum and the characterization of food coating from chitosan, zingosan nanoparticle, and Indonesian essential oil composites. This work also published in Food Packaging and Safe Life Journal. The objective of this work are to investigate the application of edible coatings comprised of chitosan, zingosan nanoparticle, and essential oil composite against Penicillium italicum, and to investigate the physicochemical characteristic of the composites. Zingosan nanoparticle were characterized for its morphology by using IFM, and the particle size distribution was confirmed by using dynamic light scattering method using zeta sizer, resulting size 154.42 nanometers. And for essential oil and zingosan nanoparticle also characterized by using potassium bromide method, FTIR. Preliminary test was carried out to determine the proper concentration of each material. As shown in this figure, 0.8% chitosan and 0.025% zingosan nanoparticle and 0.5% sandalwood essential oil was considered as the best formulation to inhibit the fungal growth. For essential oil was believed its antifungal activity because of the active compounds such as alpha xanthalol and beta xanthalol, which were confirmed and analyzed by using gas chromatography mass spectra. And then it was combined to produce coating film. They were homogenized by using ultra-thorax and vacuum degas, and then coating film characterization and fruit coating application. In vitro analysis of antifungal activity in the medium solid method resulted that the use combination approach with chitosan, zingosan nanoparticle, and sandalwood essential oil was found to control Penicillium italicum growth. significantly compared to control. And the antifungal mechanism of chitosan is explained by this figure, started from the interaction between chitosan and phospholipid of cell membrane, followed by destruction of membrane and resulting cell death. And this antifungal mechanism is strengthened by zinc oxide nanoparticle, which could contribute to resolve the reactive oxygen species and resulting cell membrane leakage, cytoplasm loss, cell structure destruction, biomacromolecule inactivation, irreversible chromosome damage, and changes in gene expression level. The coherent efficacy was shown by spore germination test. Spores germinated well in the absence of the coating treatment, while the treated spore began to germinate partially, as indicated with the blue arrow. To further understand the mechanism of antifungal, Propidium iodide test was conducted. Propidium iodide fluorescence staining is quite unique chemicals. It can bind DNA and exhibit red fluorescence, but it is incapable to enter the healthy spore due to the membrane barrier. As seen in this figure, untreated spore were not stained, whereas the dead spore were readily stained. That result was confirmed by in vivo tests on tangerine fruit. Fungal spore were first deposited on the center of tangerine fruit and then kept at 25 degrees Celsius and 80% humidity. And against the addition of zinc oxide nanoparticle and sandalwood essential oil together improved the antifungal activity of chitosan because they act as antimicrobial agents. Then for oil droplets was confirmed by using CLSM with the aid of Nile red staining. And then the interactions between each material and microstructure of the film were characterized by using FTIR and FM and SEM respectively. The coating also indirectly affects the physicochemical characteristic of fruit, especially for total soluble solid. And so in this figure, control fruit has the total soluble solid higher compared to coated fruit. Edible coatings application may inhibit the metabolic rate by lowering the internal aspiration, therefore preventing the metabolic hydrolytic changes from starch to sugar. And then this table 2.1, shows the physicochemical characteristic of the base formulation from this study. And then so far, the conclusion of this chapter that incorporation of essential oil and zinc oxide nanoparticle into chitosan showed outstanding effect on the inhibition of fungal growth. And then the addition of zinc oxide nanoparticle and essential oil affect the physicochemical characteristic of chitosan-based coating film.